Hey, welcome back to our videos for examples 2 and 3 in the describing polynomials notes. And in example 2 and 3, we're just going to be summarizing what you already learned in the Schoology Math Lab for the leading coefficient test. In example 2, we're looking at polynomials that have an even degree, and in example 3, we'll be summarizing the leading coefficient test for polynomials with an odd degree. So the leading coefficient test determines the end behavior of the graph of the polynomial. And when you look at these three examples, right, these are all even degree polynomials, right? This parabola here is a quadratic. Then we have an x to the fourth, a fourth degree trinomial, and then a sixth degree four-term polynomial example here on the end. And we can see in all three of these that they're even degree and that each one have a positive leading coefficient. Okay, whenever your polynomial has those characteristics, it's an even degree with a positive leading coefficient, the ends both face up, right? You can see that in each one of these graphs. So the ends start facing up on the left side and they end facing up on the right side. So we would record that end behavior using the notation that we learned in the last unit, that as x approaches negative infinity to the left, right, the y is headed to positive infinity. It's headed up. Then as x approaches positive infinity, now we're headed to the right end, the y is approaching positive infinity. It's heading up. Okay. Now, when we have even degree polynomials but negative leading coefficients, so you can see here this quadratic has a negative leading coefficient, this fourth degree polynomial, negative leading coefficient, the sixth degree polynomial, a negative leading coefficient. In all of those examples where there's an even degree and a negative leading coefficient, the ends are both pointing down, right? So the graph starts down on the left side and it ends down on the right side. So in our end behavior notation, as x approaches negative infinity on the left, the y is headed down to negative infinity. And as x approaches positive infinity, right, that's the right end behavior, the y is also going down to negative infinity. So things to remember about even degree polynomials, right? Both ends are going to point in the same direction. If it's a positive leading coefficient, so leading coefficient greater than 0, right, positive, then the ends both point up like the parent graph of the parabola, y equals x squared. If you have a leading coefficient that is negative, then remember a negative a, that's a reflection in the x-axis, so both ends would point down. Okay, the only time that is not the case is when the degree is 0. When you have a constant function, there is no leading coefficient test for that, because a constant function is just a horizontal line, right? So your even degree would have to be 2 or higher. So 2, 4, 6, 8, 0 won't count for the leading coefficient test. And then in, excuse me, in example 3, we're looking at what happens to the end behavior with an odd degree. So when you look at these three examples, this is linear. 2x minus 3 has a degree of 1. The next is cubic. X cubed minus 2x plus 2, that's a degree 3 or cubic polynomial. And then x to the fifth minus 3x cubed plus 2x minus 1, that's a degree 5 four-term polynomial. So in each of these instances where we have an odd degree with a positive leading coefficient, we can see that the graph is headed down on the left, so it's starting down, but on the right end, it's pointing up. Right? So these start down and end up on the right. So in our end behavior notation, we would record that as x approaches negative infinity on the left, the y is headed down to negative infinity. But as x approaches positive infinity on the right, the y is approaching positive infinity. Okay, then when we look at the next three examples, we have odd degree but negative leading coefficient this time. And in those, because there's been a reflection in the x-axis, the opposite is happening. It's starting up on the left and ending down on the right. So an odd degree polynomial with a negative leading coefficient starts up and ends down. So as x approaches negative infinity on the left, y is approaching positive infinity. It's headed up. As x approaches positive infinity, so this is the right end, the y is going down to negative infinity. Okay, so things to remember: when you have an odd degree polynomial, both ends will go in opposite directions. If your leading coefficient is positive, so it's greater than 0, like the parent graphs of the linear and the cubic functions, okay, then they're going to start down and end up, just like those parent graphs. If your leading coefficient is negative, that's a reflection in the x-axis, right? The a is negative, and so it would be the reflection of those parent graphs, and they would start up and end down. Okay, before we get started with example 4 in the notes, we're going to take a look at this question: how can we find the end behavior of each without rewriting in standard form or graphing first? So if we take a look at this equation, y equals negative 7x to the 7th times the quantity x minus 7 to the 7th power. So we want to take this binomial x minus 7 and raise that to the 7th power. Now if that was just two of them, if it was an x minus 7 times another x minus 7, right, then we would FOIL and we'd have x squared minus 14x plus 49. Then we'd have to take that result and multiply it times another x minus 7 and another x minus 7, right? So we'd have x squared minus 14x plus 49 times another x squared minus 14x plus 49. And we'd end up with this huge, huge monstrosity by the time we got all the way down to 7 of those being multiplied together. We don't need to do all that work, all that algebra, just to figure out the end behavior. So if all we want is the end behavior, we're going to ignore for the moment the fact that this is a binomial and just keep an eye on that first term in the binomial, because that's where our highest exponent term is going to come from. So that would be an x times 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 an x, right? 7 of those together. So this binomial to the 7th power is going to result in the end with an x to the 7th as its leading term. Then there's going to be, a minus and then some x to the 6th, and x to the 5th, x to the 4th, but we don't care about any of that when we're just figuring out the end behavior. So if I take this negative 7x to the 7th times the x to the 7th, the leading term of that binomial that gets raised to the 7th power, that's going to give me a first term of negative 7 and then x to the 14th. Right, negative 7 and an x to the 14th. So just with that, that information, that negative 7x to the 14th as my highest exponent term, I know that my degree is even, and I know that my leading coefficient is negative, right? Now, that is enough to tell me that both ends point down in this polynomial because of my leading coefficient test that we looked at in example 2 and example 3 in the notes. So my end behavior would be written that as x approaches negative infinity on the left, the y is headed down to negative infinity. And then as x approaches positive infinity on the right, the y is still headed down to negative infinity, right? That's the notation for the end behavior where both ends go down. Okay, now in my next example, y equals x squared times the quantity x to the 3rd plus 4, and that's raised to the 5th power. I have the same situation as before where I am multiplying a binomial times itself 5 times. So I would have an x to the 3rd plus 4, and then that would be times another x to the third plus 4 times another x to the third plus 4, and so on and so on. And I don't want to multiply 5 of those together. I just want to keep an eye on that leading term and what happens to it as I multiply. So an x to the third, if I multiply 5 of those together, I would have an x to the third to the 5th power. So we would multiply the exponents, and I would end up with an x to the 15th as my highest exponent term from that binomial being raised to the 5th power. Then that's times the x squared that was in the front there, and I'd add those exponents and get an x to the 17th as my highest exponent term. And that would be all I'd need to know in order to say that my degree is odd. So odd degree and a positive leading coefficient. That M behavior we learned in example 3 with the leading coefficient test starts down on the left and ends up on the right. So as x approaches negative infinity, that's heading to the left, my y is approaching negative infinity. It's heading down. Then as x approaches positive infinity, that's headed to the right, the y is approaching positive infinity, heading up. Okay, so then looking at this third example, I've got negative 4x, that quantity is being raised to the 4th power. Okay, and when you raise a quantity, a monomial, to an even exponent, right, that negative is going to become positive because I have a negative times a negative, another negative times a negative, right? These two make a positive, these two make a positive, and positive times positive is positive. So this will become a positive. Oops, too big. Okay, that's going to become a positive, and then the 4 to the 4th power, that is equal to 256, and then my x to the 4th power will follow. Okay, so negative 4x, that quantity to the 4th power, is a positive 256 x to the 4th. Now after that comes a minus, and then the binomial x minus 4 is getting raised to the 4th power. So remember, we're not going to FOIL that all out 4 times. We're just going to keep an eye on that first term, right? And that x is going to get multiplied times itself 4 times, so that's an x to the 4th. Then I'll have a minus multiplied in front of it, so that'd be a negative x to the 4th. And 256 minus 1 is 255. So now I know that my term here, my highest exponent term, is 255 x to the 4th, right? There'll be a whole bunch of x cubes and x squareds and stuff that follow, but all I need is that first term to figure out the end behavior. So my degree is even, and my leading coefficient is positive. So an even degree and a positive leading coefficient, both ends are facing up. So as x approaches negative infinity on the left, the y is headed up to positive infinity. And then as x approaches positive infinity on the right, the y is still headed up to positive infinity.